Let's go beyond just 2 quantum bits. We're going to copy this code from Python code to measure a quantum computer into a Colab notebook. But this code, it's only got 2 quantum bits. And yeah, sure, it entangles them in a nifty way so that they represent a Bell state where they're both always 0 or they're both always 1. And they're like Schrodinger's cat, a superposition where they're both always 0 and both always 1 with a 50-50% chance, and that's what they are. That's how they exist. Now, what happens if we put a third, let's call it Schrodinger's stray cat, into the circuit that's not entangled with the other 2? How does that affect our bar chart, our histogram? Let's see. Okay, so we've copied this code from YouTube. I'll put it in the description of this video also. We just pasted into a new notebook. I'm going to call this adding more qubits, and we'll just hit play just to make sure that this code works. The H gate puts the quantum bit at index 0 into superposition. The CX gate entangles it with the quantum bit in index 1, and then we measure quantum bit 0 into classical bit 0 and qubit 1 into classical bit 1, and simulate a quantum computer and display the histogram in the circuit. So currently we're only going to have 2 bars on our bar chart. We've got the one representing 0, 0 and the one representing 1, 1. And we see we've got our 2 quantum bits in our circuit getting measured into a classical bit. So let's add a third qubit. We do that by changing this 2 in QuantumCircuit 2.2 to a 3, and we'll change the other 2 to a 3 as well. But now that we've got 3, we want to measure all 3. So it's 0 index. The first one goes in index 0, and then the second goes in index 1, and the third in index 2. So I'm going to add a comma 2 at the end of the quantum bit array and the classical bit array that they get measured into as we pass those into circ.measure. Okay, let's test that code out. Now we have a 3 qubit quantum circuit, but we're not doing anything to the new third qubit, right? The quantum circuit initializer here, it sets them all to 0 unless you give it other initializers. They'll all be 0 when you first create the quantum circuit, or ket 0 to be exact. And so here's the new one. We still only have 2 bar charts, or excuse me, 2 bars on the bar chart. And the new one that we have is at the beginning. Well, why is it at the beginning, I wonder? We put it at the end, right? Yeah, they drew it backwards. The histogram labeler in Qiskit just puts the last one first for some reason. So the newer ones we're adding are going to go kind of at the bottom here of the labels. And we see we have Q0, 1, and 2 in our circuit, and that Q2 isn't getting anything other than a little gas gauge. It's not part of any circuit. All it does is get measured. That's Schrodinger's stray cat. Okay, so without being entangled with the other 2, we can still put it into superposition with circ.h, and we're going to pass it 2 because the new one is our qubit number 2. Now we'll want to do that before we measure, otherwise it's not going to actually make it into the histogram. So it looks like this. We put 0 into H, entangle it with 1, and then we put 2 through an H. Now this is going to give us some extra bars in our bar chart, but it's not actually going to make the bar chart that interesting. They're still all going to be really even, because this one isn't really mixing with the others in any way. It's not entangled with them at all. Yeah, so it adds the 0s and the 1s to the already existing 0s and 1s. So all the ones where the Bell state came out to a 0, that's this one here, the first one and the third one. And then the ones where a Bell state came out to a 1 are this one and this one. but the new qubit also can come out to a 0 or a 1. So it's like flipping a coin twice. We have 4 possibilities. One of those coins just happens to be a Bell state, and the other happens to be a single qubit. But it still doesn't make a very interesting histogram. This is going to get really good really fast now. We're actually going to be able to draw bars of different sizes using a quantum circuit and probability, and we're going to do partial phase gate rotations around the block sphere. Check it out. Then, how do we achieve these bars of different sizes? Here's the block sphere. Think of this as a globe on the surface of your desk. On the North Pole, we've got 0, and on the South Pole, we've got 1. Everything on the equator is halfway between the North and the South Pole, so everything on the equator is halfway between 0 and 1. Now, it doesn't matter where on the equator it is, it's still going to be halfway between 0 and 1. But we have this diagonal gate called the H gate that rotates it around in such a way that its position on the equator then influences its latitude, or its probability of being measured. In other words, the phase angle phi will affect the probability angle theta if you rotate it around the equator and then pass it back through an H gate. So let's check it out. We've got our circ.h2, and we're going to pass that through circ.t. T is also called the pi over 8 gate. You can see it says it performs a pi over 4 rotation, but pi over 4 radians is 1/8 of the way around the sphere, because 2 pi is the full distance around a sphere in radians. And then, after it goes through the T gate, we got to pass it back through an H gate again. So that's the trick. Put it in superposition and then rotate it around the sphere only a short distance. That's what T does. And then put it back through an H again, taking it out of superposition. And then we're going to measure. This symbol is the capital Greek letter phi. Most block spheres use a lowercase phi. The theta is always capital, and that's the angle that measures the probability of measuring a 0 or a 1. But once you change phi, then pass it through an H gate, the resulting theta is different. As you can see, we now have bars of different sizes. And our circuit looks a lot more complex. So it goes H, T, H. Now there's other stuff we can do besides just passing through a simple T gate, but that's one of the secrets to the types of quantum algorithms that get interesting results. And we'll explore them in more detail as we continue on to make this easy.